Hello, everyone. My name is Vardan, and I'm from Stanford. I'm a postdoc that is advised by David Donnell. So let's begin with the outline of today's talk. I'm going to start by talking about rough landscapes in deep learning. I'm going to focus on the Hessians in deep learning, and I'm going to show some measurements of these Hessians at large scale on real data. And I'm going to conclude by talking about the structure in the outliers of the spectrum of the Hessians. So Deepnet loss surfaces have rough landscapes, as the title of this workshop suggests. However, the traditional notion of landscape suggests that someone is exploring the whole spectrum, the whole landscape. However, in deep learning, what usually happens is you run SGD, you converge to a certain solution, you observe a certain behaviors along the path of SGD, but there is no real exploration of the whole landscape. In this talk, I will not talk about the global topology of the landscape, and I will also not talk about the path of SGD. I'm going to focus on the converged solution of SGD, and specifically about its Hessian. So the first mention in the literature, or at least the most popular mention in the literature of Deepnet Hessians, is the work by Hochreiter and Schmidhuber, which is called flat minima. And in that work, they make this claim that flat minima of the landscape tend to generalize better. So this was in 1997, and 2 decades later, we can still see empirical works that are trying to assert their claim. So let me give you an example. Imagine that you're trying to train a network and you're using a certain batch size. The bigger the batch size, the faster you're going to be able to train the network, because you can parallelize over more GPUs. But there is an issue, and the issue is that once you increase the batch size, at a certain point, your generalization performance deteriorates. So people are actually curious, why does that happen? And these 2 empirical works that appear up there are basically saying that large batch SGD converges to sharp minimas, and based on the 97 work over there, we know that sharp minimas lead to worse generalization. Now, I would suggest everyone to take all of these statements with a grain of salt, because in a recent work, it was actually shown that most of the notions of flatness that people are using in deep learning are problematic, in the sense that you can take a flat minima in the landscape, you can reparameterize the parameters of the network without changing the actual function that it's creating, and you can actually create a sharper minima. So the takeaway is that the landscape is or the flatness of the landscape is related to generalization, but it's currently unclear what is the exact relation.
Sorry, can I just ask
Yeah.
on this?
Yeah.
Forever. If you constrain your weights for each node in the network,
Yeah.
with a spherical constraint, so to avoid this kind of reparameterization.
No one does that.
No, wait a moment. Well, if you do this, at least analytically,
Yeah.
you get rid of this rescaling, and so what remains is what is really interesting.
But there could be other types of symmetries, so to speak.
It could, but
this is not so straightforward, because it really depends how you constrain. So you suggested one way of constraining, which is constraining the
volume in the weight space.
Sorry?
Constrain the volume in the weight space.
What do you mean by volume in the weights? You suggested looking at the weights and constraining the L2 norm of each unit. Okay, so, but there are many other ways of constraining. It could constrain the overall L2 norm, it could constrain the overall 1 norm, right? Each one of these would lead to a completely different notion, completely change what it means to be sharp or flat.
I agree with Nati.
So
Can we?
you could say, well, if you just constrain it, then the notion is well defined.
Yeah, maybe we can continue and discuss this offline, or not.
In many different ways.
Some authority is needed. So I stand here. Can you hold the stick or something? Okay, so I'll continue with the work which is called 3 Factors Influencing Minima in SGD. And what they do is they continue this trend of saying generalization is predicted by the flatness of the landscape. And they claim that they can predict the flatness as the ratio of the learning rate to batch size. So what does this mean to me? It means that if you're in the business of trying to speed the training of SGD, and you're trying to find the optimal hyperparameters, you're tuning certain knobs, then you probably should care about how the flatness of the landscape behaves like. There's other examples of similar works. For instance, this recent work by OpenAI that tries to predict the largest useful batch size of SGD prior to the deterioration that I previously mentioned. And what's interesting about this work is, again, that their largest useful batch size is a function of the Hessian. And we actually saw a different work today by Shao, who presented a similar type of concept of how can you tune the learning rate optimally in order to obtain good performance of SGD. There's another interesting work that was mentioned yesterday, which is called entropy SGD. And there the authors propose a modification to SGD that would favor flat minimas. And there's yet another different work, which is called gradient descent happens in a tiny subspace, where the authors are making a claim that the gradients of SGD are apparently living in a very tiny dimensional subspace, which is spanned by the top eigenvectors of the Hessian. So if you're in the business of speeding the training of SGD, then you might as well take into account those top eigenvectors somehow. And the last relation is the relation between landscape and some optimization guarantees. And the most famous work on this topic is the loss surfaces of multilayer networks, where they show that the loss critical values of the loss of deep nets are located in a certain band around the global minima. And once you go outside of this band far away, then the number of local minimas vanishes exponentially with the dimension. What's interesting about this work is the set of assumptions they've actually had to make, specifically about the Hessian of the network or the weights, in order to obtain this theoretical claim. And you can see other types of examples. For instance, this work by Yasaman, who's actually here, which is called Geometry of Neural Network Loss Surfaces via random matrix theory, where they show that the number of negative eigenvalues of the Hessian can be predicted as the power of the energy, basically the value of the loss, to a certain power. So this is another example of how people are making certain assumptions about the Hessian in order to make certain optimization guarantees. So I just quickly surveyed 10 works on deep learning, and there's one thing which is in common in all of them. All of them relate to Hessians. And basically, what you can see is that the properties of the Hessian are crucial to generalization performance, the training speed of SGD, and to optimization guarantees, right? And this leads to the following observation, that the Hessian of today's deep nets are actually enormous. They're of size tens of millions by tens of millions. And they were actually never previously studied at this full scale. So today's question is, what do we actually know about the Hessians of deep nets? So if I tell you, close your eyes and imagine a deep net Hessian, what do you see? So let me show you what you might possibly want to imagine in your mind. So this is a set of slogans about the eigenvalue distributions of deep net Hessians, and I'm going to show you later empirical justification for each and every one of them.
That's about the Hessian along the trajectory of the...
No, converged solution. Only converged solution.
Converged solution with that.
At the end of SGD, after a certain number of epochs. Supposed convergence. Supposed convergence. I'll get to that. So that's point number 2. You can actually, it's a point along SGD, and you can look at different points. So first of all, you can see that the spectrum of the Hessian has a bulk distribution. You can see immediately, as was observed, that the Hessian has many negative eigenvalues. You can see that there is outliers in the spectrum, and if you count the outliers, which I have, you can see that the number of outliers is approximately equal to the number of classes. Finally, you can see that there is a certain property of scaling of the outliers as function of training or sample size, where the outliers are being separated from the bulk. So this leads me to my next section, which is called Measurements of Hessians at Large Scale. So I would like to start by mentioning a work which is called Empirical Analysis of the Hessian of Over-Parameterized Neural Nets by Sagun and co-authors. And this is basically the first work that studied the spectrum of deep net Hessians. And what they did was a beautifully simple experiment. So they sampled a 100-dimensional Gaussian mixture model with varying number of classes, and then they just trained at 2 hidden layer neural networks with 30 hidden units in each layer, followed by a classifier. Then they took the network and they computed the spectrum of the Hessian, which is what I'm plotting you here. So this is a scree plot that shows on the x-axis the number or the index of the eigenvalue, and on the y-axis you have the value of the eigenvalue. Each color corresponds to a different number of classes. And what you can see here is a separation of the spectrum into 2 parts. The first one is the bulk, which is here, and the second part is the outliers above. If you were actually, if you counted the number of outliers, you would see that they correspond to the number of classes. And you can also show, if you go beyond this plot to much larger indices, eventually you get negative eigenvalues. So when we saw this work for the first time, we were curious as to whether this is a phenomenon that is due to the simplistic assumptions they've made about the data, a 100-dimensional Gaussian mixture model, or the simplistic assumption they made about the network, 2 layers with 30 neurons each, or it's an actual phenomenon, right? So if I train a ResNet or a VGG with 30 million parameters on MNIST, CIFAR, or ImageNet, would I actually see the same phenomenon? So this led to a recent paper, which is called The Full Spectrum of Deepnet Hessians at Scale, Dynamics with Sample Size, which appears on arXiv, which shows the answer to this question. So I'm going to just jump straight ahead to the results. So here I'm showing you the train Hessian of VGG11, which has 28 million parameters on different data sets. So you can see MNIST, you can see Fashion MNIST, you can see CIFAR, and CIFAR 100. Each panel here shows on the x-axis the eigenvalue, and on the y-axis the density of the spectrum on a log scale. And what you can immediately see is that the spectrum consists of a bulk distribution plus a set of outliers. You can see that the spectrums have negative eigenvalues. You can see that the number of outliers is approximately equal to the number of classes.
Just a silly question. Why instead of one point I see a bump where there is an outlier? You are convolving with a curve?
So it's related to the method we're using. It will become clear later, hopefully. But yes, what you just said, basically. Okay, so this was the train Hessian, which means that it was computed on the train data. And now I'm going to show you the test Hessian. So, oh no. Oh, okay. So the test Hessian of the same architecture shows a very similar type of bulk plus outlier structure. But there's a big difference between the two. The difference is that if you look, for instance, here, you can see that some of the outliers are now inside the noise, inside the bulk. Whereas in the train case, all of the outliers were outside. So by shifting from the training data to the test data, you basically, some of the outliers get pulled back into the noise. Okay, so next we would like to understand the properties of this Hessian, the outliers, and the bulk. So what we do is we do a decomposition of the Hessian into 2 components. One of the components is called the Hessian of predictions. We denote it by H. And the other component is called the covariance of gradients, and we denote it by G. Let me explain some of the notations here. So you can see here there is an F. F are the predictions of the network, and they're basically the output of the classifier prior to the softmax. And they're called in deep learning jargon logits. Theta is a vector, very long vector, of all the parameters in the network concatenated. So it's, let's say, 30 million in length. And the L over there is the loss of the network. For instance, it's cross entropy plus softmax. So you can see that the Hessian of predictions is just the second derivative of the predictions times the first derivative of the loss, while the covariance of the gradients, G, is the first derivative of the predictions times the second derivative of the loss times the first derivative of the predictions. And the question that I'm interested in is whether I can attribute the outliers and the bulk to one of these matrices. Can I say that the bulk is due to H or G, or the outliers are due to H or G? So this leads me to this experiment. So here I'm showing you the spectrum of the Hessian in the first row, the spectrum of the G, which is the covariance of the gradients, in the second row, and the spectrum of H in the third row. And again, the x-axis is the eigenvalue, and the y-axis is the density of the spectrum on log scale. And what you can immediately see is that the outliers that you observe in the spectrum of the Hessian appear also in the covariance of the gradients, but they do not appear in the Hessian of predictions H. So we can safely attribute the outliers to the G term in the decomposition.
Could you show again the G and the H?
Yeah. So H is the second derivative of the logits, or the output of the classifier, and G is just the covariance of the gradients. Next, what I'm going to do is I'm going to zoom in on the range 0 to 100 on all of these plots, and I'm going to show them on the same figure. So what you can see here, again, x-axis is eigenvalues, y-axis is density of spectrum. In red, I'm plotting the spectrum of the Hessian. In green, I'm plotting the spectrum of G. And in blue, I'm plotting the spectrum of H. And what you can immediately see is the alignment between the Hessian and the H term. For instance, you can see it here. Notice how similar they are. So basically, what this means is that you can attribute the bulk of the spectrum, which is basically this part, to the H term. Ask if you have questions, if I'm not clear. Okay, now at this point you might be wondering, can we actually say something about the distribution of the bulk, right? So here in this plot I'm showing you the eigenvalue versus the density of the spectrum. Both of them are on a log scale, so it's a log-log plot. And I'm fitting a line to the distribution, and this line fits very well with an R² of 0.98. And what it shows is that the distribution of the eigenvalues of the spectrum, of the bulk, of the spectrum, is basically following a power law. Why is that interesting? Because the first thing that people assume once they do theoretical works on this is that the distribution of that is something like a Vischer distribution or a Marchenko-Pastur distribution, which is definitely not the case on trained nets. Okay, so the original motivation for studying the spectrum of Hessians, or at least the main one, was to understand generalization. What does it mean to understand generalization? It means to understand how does the deep net behave as function of training sample size. So what I'm showing you here is the train Hessian and the test Hessian as function of sample size. So the first column corresponds to 10 examples per class, the second to 50 examples per class, and the last to 506 examples per class. And what you can see is that once you increase the number of examples, then initially you have 6 outliers in the spectrum, then you have 7 outliers in the spectrum, and finally you have 10 outliers in the spectrum. So basically the outliers are getting pulled away from the noise with increased sample size. Yeah?
So you said this is at some point during the training trajectory?
At the end of the training. After 300 epochs of SGD.
Okay, so this is
Yeah. And you retrain it for 10 examples per class, 50 examples, and 500. Separate training.
And what is the test Hessian?
The test Hessian is the Hessian computed on the test data. So mostly when people talk about Hessians, they talk about the Hessian of the training data, which is computed on the training, the training data. But this is the test data.
So the scale is also reducing. It's becoming flatter as you increase the number of training samples.
You're talking about this quantity?
Yeah.
Or
more especially in the top.
I would rather not comment. I'm not allowed. So it seems, yes. So it seems.
But you don't put much stock in it. So.
I didn't renormalize everything beyond the trivial normalization of the Hessian being the average of second derivatives.
I see.
But
So the question is, when you define the loss, you define it with the 1 over n?
Yes. So, yes. Okay, so what we saw up to now is that the outliers are induced by the G term, which is the covariance of the gradients. The bulk is induced by the H term, which is a Hessian of predictions. And the tail of the bulk follows a power law and not a classical random matrix theory type of matrix. And the natural question to ask at this point is, how did we actually make these measurements at such a massive scale? So here are things we did not do. The first thing that you would perhaps suggest is using a power method.
So, I'm sorry.
Yeah,
the
sorry.
power, what was the power?
2.6, minus 2.6. Is that a good power? It says something to you?
The Gaussian ratio.
Okay. So the first thing you might want to do is use a power method, but that is insane because that will get you one eigenvalue out of 30 million. The next thing you might want to do is use a subspace iteration, which is like using power method, but on a subspace larger than 1. But that will give you 10 eigenvalues out of 30 million. And you might want to do SVD, but SVD can only work on Hessians of size, let's say, 5,000. If your patient may be larger, but it doesn't get you all the way to 30 million parameters. So how did we actually manage to compute the spectrum of the Hessian? A secret. So, no, I will tell you. So in the 1970s,
Would you comment on that?
no, in the 1970s, there were many smart quantum mechanics and physics who were studying the energy level of different Hamiltonians. And they were basically computing the spectra of large linear operators. And we leveraged those ideas to approximate the spectrum of the Hessian. And there's a very nice paper by Yusuf Saad and co-authors, which is cited here, which explains some of these algorithms that were used back in the days, the good old days. So specifically what we did was we used the Lanczos algorithm, and a short explanation of what this algorithm does. So the Lanczos algorithm takes the Hessian, which is a huge linear operator, and constructs an adaptive orthogonal basis that three-diagonalizes this matrix. Given the three-diagonalized matrix, you then compute its eigenvalue decomposition, and based on this eigenvalue decomposition, you construct the approximation to the spectrum. So we implemented all of this in PyTorch. PyTorch is missing. And there's many non-trivial engineering tricks. For instance, if you try to compute the operator that multiplies, let's say, a vector by the G term or the H term, that's like easily 3 days if you know PyTorch. If you don't know, Godspeed. And we plan to release a package so that anyone would be able to compute the spectrum of their Deepnet Hessians. PyTorch appears. So the complexity is similar to training a model, so anyone who can actually compute, anyone who can train a model can compute the Hessian spectrum of that model. Okay, so the last part is called structure in the outliers. And why do we care about the outliers in the spectrum? So we know the outliers are due to the G matrix in the decomposition, and we know that the only eigenspace that actually generalizes is the outliers of the spectrum. What does that mean? So the spectrum has outliers and noise. The noise actually has no meaning. The outliers are things which correspond to actual classes, right? Now, as I mentioned, there was a recent work that suggests that SGD is trapped in a certain subspace. And based on the empirical evidence I've showed you, you can conclude that this subspace is in fact the outlier subspace. So this naturally suggests that we should understand this subspace better. So here are certain insights that I will go over more in detail in the following slides. So first of all, I'll show you that the gradients have in fact some structured means. I will show you that this mean structure in the gradients creates the outliers that you see in the spectrum. I'll then show you that the outliers in the spectrum cause the optimization to happen in a low-dimensional space, which means that SGD is basically optimizing a network of 30 million parameters in a C-dimensional space. Just let it sink, right? You're wasting billions of dollars on training networks using SGD. SGD is operating in extremely high dimensions, but it's in fact only moving in a very tiny subspace, which suggests that we can probably improve SGD somehow. So again, what is causing the outliers to appear? That's the topic of a recent paper, which is called the three-level hierarchical model for the outliers in the spectrum of Deepnet Hessians, and it will be posted on arXiv soon. So I'll show you now 3 different observations that will explain why are there outliers in the spectrum. The first observation is that the gradients of the loss have a certain structure on their indices. So define delta k to be a certain gradient induced by a certain element. So k is actually an index which has a 3-tuple structure. So it's basically indexed by 3 numbers. The first number is the index of an image. So imagine you have a bunch of images of cats. So I corresponds to the 5th cat, for example. C is the class of the true class of the image. And C prime is a potential class. So it's one of the capital C different classes that every image could be. And there are a total of I times C elements, where I is the number of images and C is the number of classes. So we define delta CC prime to be the average of all of these delta CC prime I elements, where we're averaging over all the i's for a certain fixed C and C prime. So delta CC prime is basically a certain mean, and sigma CC prime is the covariance that corresponds to this mean. And the idea is that the gradients are basically sampled from the Gaussian mixture model, which is defined by these means and these covariances.
I'm sorry, I haven't understood who C prime is.
So C prime is the index of a certain classifier in the network. Imagine you have an image of a cat and you pass it through a network and you obtain a set of C predictions. Then C prime is the index of a certain prediction. It corresponds to a logit that is produced by a certain example. Okay, the second observation is that G is a second moment matrix. And what this says is that G can be written as a summation of outer products of these delta K entities. And based on the first observation, we know that the K is a tuple over 3 elements, C, C prime, and I. So then we get this. And then the third step is saying that this is a second moment matrix that can be decomposed into a mean and a covariance. Okay, so this is the second part. And the third realization is that the means here, this is a mean matrix which has structure in itself. And you can view these means as being realizations of a different Gaussian mixture model which has these means delta C. So here's the picture. You have gradients on the first level. You sum a bunch of gradients, you compute their average, and then you get the second level, which is delta C, C prime. And then you sum over C prime, and then you get delta C, which is the highest level. It's a 3-level hierarchy. And let me just jump straight to a visualization that would explain the structure. So here I'm showing you a TSNE visualization of the delta C and the delta C, C primes, where the bigger circles correspond to the delta C. So that's, for example, a delta C that corresponds to frog. And the smaller points here and there correspond to the delta C, C prime. What you can see is that the delta C, C prime are basically scattered around the delta C. Okay, this is the first plot. And the second plot is showing the actual, what is the point of this decomposition. The point is the following, that what you can do given those delta C's is you can compute a C by C matrix that is, let's say, 10 by 10, that is constructed from those means, and then you can compute the eigenvalue decomposition of that. And the main claim in the work is that the outliers in the spectrum are the eigenvalues of this 10 by 10 matrix. So here what I'm showing you is, again, on the x-axis eigenvalues. On the y-axis is the density of the spectrum on log scale. And what you can see in blue is the spectrum approximation of G using Lanczos. So this is the first part of the talk. And in orange, what you can see is the 10 eigenvalues that are obtained from the rank 10 matrix of the different means on the highest level of the hierarchy. So just to emphasize, you don't need any fancy linear algebra tools to compute the location of all of these outliers. You just need to compute means and a 10 by 10 eigenvalue decomposition. So obviously there's a relation here between these measurements and random matrix theory. And the closest model to this one is called the spike second moment matrix model, which basically assumes that you have a matrix of the type P plus ZZ transpose, where P is a low rank matrix and Z or P are orthogonally invariant to each other. It's not really what we have, because in our case we have a 3-level decomposition, so there is a summation of 3 elements, but it's pretty close. So let's summarize what we've seen today. So I've shown you measurements of spectral distributions of Hessians of modern deep nets on real data. We saw that there is a bulk in the spectrum. Yeah, sorry.
In this paper that you just mentioned, you have the condition, the outlier that come up.
Yeah.
But the bulk doesn't have a tail.
Does not have?
Power law.
Yes, that is correct. Yes, 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 yes. That's why I said it was close. I need something, yeah, yeah. We do need something. More than one thing even. There's other issues as well.
Sparse? Could sparsity be anything? Some sparse random matrices that work well.
Amen. Yes, possibly, yeah. Possibly. That would be my first guess. So.
No, but since you have
Yeah. Thank you for the question. So we saw that there's bulk, there's negative eigenvalues, and there's C outliers. We were able to show that the bulk and the negative eigenvalues are due to the H matrix, which is the Hessian of predictions, and the outliers are due to the second moment structure of G. And we also were able to say that the outliers are due to a certain mean structure that was not subtracted from the G matrix. So basically, the means in the second moment matrix are creating the outliers. And it seems like there are exciting opportunities for speeding up optimization by using these observations. And we are aware of Google researchers who are actually working on this as we speak. For instance, Beruz, Gurbani, and his team. Thank you.
Now we have questions.
So this for the bulk again, which
Yeah.
might not be the most important question. Of course, the outliers are important. So you say it's coming from the H.
Yes.
And
Mostly from the H.
do you have any? So you described the structure of the G that could give the outliers.
Yeah.
Do you have any understanding of? Because of course you could have power laws. I mean, in random matrix you do have power laws. You don't only have Wishart or Wigner. You could have if you had power law entries, for instance.
Yeah.
So do you understand a little bit what the H matrix is in a decent model?
So a very simple observation would be.
Can we create this power law?
No, not yet. It's work in progress, but one thing that's trivial about the H is that you understand why there's negative eigenvalues. So, yeah, that's clear. No, so not to your question. Not yet.
So interesting. I'm curious. So you look at things at the end of optimization. Do you know if you get zero training error in this case?
Yes. Yes.
And if you don't, in cases where you do not get zero training error, or alternatively, if you look at what happens well before you get zero training error in optimization, do you still get these similar behavior with either the outliers or this clustering that you showed?
I didn't study extensively, so I would not comment. But based on the work which is called gradients live in tiny subspaces, their empirical measurements suggest that yes. They suggest that there are outliers, and from my experiments, I believe that there are negative eigenvalues, and there's a bulk as well. And there's claims in the literature that the bulk disappears. The negative part of the bulk disappears once you converge. I've seen this type of, yeah. I see exclamation.
Well, You don't converge, right? I mean, you're looking. So what's the? Maybe I should start. What's the loss?
Making such claims.
What's the loss? What's the loss
in the literature?
Right. What's the loss function?
Cross entropy.
Right. So you don't converge, right? If you're separable. So what I'm a bit trying to figure out, you diverge. You're going to go to infinity. So the scale of everything is going to go to infinity. And so what's going to happen at the end regime? So you don't converge. Right? You're going to diverge to infinity. And so you're going to diverge to infinity in some direction.
I don't understand. Why would I diverge to infinity?
Because the cross entropy loss if you're separable is.
But your weight decay.
Oh, you didn't say that. Okay, so how much weight? So in that case, depending on your weight decay, you're going to go far from. Okay, that might. Okay, so then you're all rest on how much weight decay you had.
Yeah.
The translation weight decay means
L2
L2
squared loss. Yeah.
So I was wondering, how much do you trust your methods that compute 30 million eigenvalues? I mean, did you benchmark it? How precise is this?
I did benchmark it, but I didn't actually attach benchmarks in the paper, but I do have simulations that show it's precise. I believe there's theoretical results on that as well that are found.
How precise, or I mean, on what size could you benchmark it, and how?
So I can do a very simple test, which is you compute the spectrum of the Hessian and you use a par method or subspace iteration to compute the top C eigenvalues, and you compare the two and you see very, very strict alignment. So at least the top C eigenvalues align perfectly, and I checked it for simple examples as well, like a random matrix plus a bunch of outliers. You can, of small size, you can actually compare the spectrum to the spectrum obtained from SVD. Sorry.
So just a quick, so it's very interesting practical tool. And so did you check what happens with different algorithms, say SGD or SGD plus something which improves generalization? So
no. Our main focus was on trying to understand generalization as function of sample size. That was the main thing we worked on. What would you suggest for us to check? Do you have
let's say you add the dropout or don't, so that two algorithms that have definitely different generalization patterns.
No.
Just to see the effect of the edge.
Yeah.
Did you study partial Hessian, meaning, for example, if you consider, for example, just the parameter on the last layer or the parameter, per layer to see things change?
Should I answer this? Okay. Yes. I'm not. Yes. Very interesting.
I had a similar question, but in the other direction. If instead of I'm still trying to understand what SGD does better than the rest.
Yeah.
And so if you do something more naive, more stupid than SGD, a Langevin type thing, you could also, since you have now this package, compute the Hessian and see if you see the outliers and all that, which is of course what Levent was, what we said in this work was Jan kind of, and what Levent tried on a much smaller scale. Levent Sagoon. So here. Have you tried to be?
No.
Because it would be really, it's for me at least, it's still a mystery why SGD, or what the batch size you've chosen, and when is it that this SGD is really better by finding more outliers, say than Langevin or gradient descent. You could do that in fact in this case.
Yeah. There's many different questions that we could ask and probe using this tool.
Okay, I'll allow one question first.
So I have two, so I have to pick. Did you explicitly correlate features of the Hessian with generalization? Were there any interesting correlations that you found?
Did I explicitly try to correlate features of the Hessian with generalization.
Of the spectrum.
I'll divide the answer into two parts. The first part is other people who claim they managed to obtain that, and the second part is me. I have not seen it, and I understand why. There's a certain issue that you train a network and you converge to something, and then you train on a different sample size and you converge to a different place, right? And you need to somehow align the different spectra with each other. And I found that to be non-trivial. When you see in the literature people who are making claims about flatness as versus generalization, they always make it on examples as function of epochs. And then I find that a lot more easy to believe. I think I can make up a million different types of measurements that would align with generalization. But as function of sample size, I find it more hard to see the relation.
I have a provocative question, sorry.
Sounds good.
Could it be that it is, I mean, it's very interesting, but could it be that it is a tautology?
What is?
In the sense that it might be that the Hessian is dominated by what happens in the last layer, and because you are training, you are using neural networks on a database where it works,
yeah.
Then it has to identify the correct number of classes, and this domination by the last layers will automatically get out of the spectrum the outliers. Is that what is happening, or is it
so
deeper
actually
than that?
In the work that I mentioned, tiny subspace, they actually checked this, whether the Hessian is being dominated by the last layer, and they found that it is not. I agree that obviously there's a relation between the last layer and the Hessian spectrum. I haven't seen anyone who made the relation clear. The most trivial thing you could say is something like the last layer is, it's kind of like eigenvalue interlacing maybe, in some sense, where the last layer is somehow hidden inside the Hessian, and as a result you have a submatrix, which is a part of a bigger submatrix. So there's a relation between the eigenvalues and so on, but I haven't seen anyone who talked about it or done anything. I don't think it's a tautology because I haven't seen anyone who did it or claimed it or showed that it's a tautology. Like tautology means equality. Can you prove to me that the eigenvalues of the last layer are the eigenvalues of the Hessian?
Okay, one last.
Last question maybe. Even at initialization, t equals 0.
Yeah.
I mean, you would from your argument, you would also expect those outliers, no? Just from the structure of the data.
There's actually empirical evidence that show that there is no outlier structure, if I remember correctly, at initialization. And if there is one, it's due to the architecture being a good feature extractor, even with random weights, which is, I think, a known phenomenon. But that's kind of like poetic, you know.
I mean, because even at initialization, you should have those mean gradients that may not be 0, and therefore...
Oh, you mean the last part?
Yeah, your outliers, yeah.
Oh, in the last part should be at convergence. If you're not at convergence, then computing the outliers in this way might not be a good idea.
Why?
I can explain offline. It's non-trivial explanation.
Okay, we thank the speaker again.
Thank you.